So from the previous class on the construction of the atom and atomic notation, you've probably already deduced that the elements in the periodic table are arranged by their increasing atomic number, or the number of protons in their nucleus, represented by the letter Z. The periodic table, however, a thing of absolute beauty, there's so much more to it than the atomic number. Let's put on our history caps again and think back to the late 1800s, specifically the 1860s. This occurs somewhere between Dalton's atomic theory and Thomson's cathode ray experiment, right smack in the middle of the Industrial Revolution and the dawn of the Civil War in the United States. The big debate in the scientific world, which at that time was Europe, was how do we arrange and classify the known elements? You can think of it as trying to assemble a puzzle, but without the corners and notches that give you the hints as to where to put the pieces. At this point, there were approximately 60 elements, and we knew most of their atomic weights. Scientists had already went for the low-hanging fruit, or sorting the elements in terms of their increasing atomic weights. However, they noticed that some groups of elements had similar properties, but most of these properties had no relation to the atomic weight. For example, lithium, sodium, potassium, and rubidium tend to react with fluorine, chlorine, bromine, and iodine. They also burn in the presence of water. Beryllium, magnesium, calcium, strontium, and barium were similar but less reactive. Scientists noticed what we would call periodic behavior, or the reactive characteristics would repeat every 7 elements. But what stunned scientists is that once they got to the elements with a bigger atomic number, the periodic behavior deviated from the 7-element repeat. This became one of the hot debates of the 1860s, how to arrange the elements in a way that accounted for both their composition and reactivity. Some scientists were happy to accept the imperfections of the periodic system, but the Russian scientist Dmitry Ivanovich Mendeleev was not satisfied and eventually figured it out, because he realized that there were holes in the table for the elements that weren't discovered yet. Once you accounted for the holes with the undiscovered elements, the periodicity of 7 elements worked out. Later, those elements would be discovered, and Mendeleev was proven to be correct. Mendeleev's periodic table, which we now use as the gold standard, arranged elements off both their atomic number and their reactivity. Periods, which are the horizontal groupings on the periodic table, arrange elements in terms of their atomic weight. Going from left to right, we increase Z by 1 unit, or 1 proton, between each element. Groups are the columns, or vertical groupings, that cluster elements together based off their similar chemical and physical properties. As you go down the group, the Z increases. Now, we'll take a look at the periodic table and annotate it for our future use. So, our periods are grouped by Z, and Z increases by a factor of 1 for each proton, from left to right. Our groups are our columns. They're given numbers, and in some cases, special names, due to the shared properties of the elements within groups. Let's get to know some of our groups. The first thing that we'll note is hydrogen, although listed above group 1, is not a part of group 1. To quote the Skeletons in the David Pumpkins Saturday Night Live sketch, hydrogen is its own thing. Below hydrogen, lithium, sodium, etc. are the group 1 or alkali elements. One bump over to the right is our group 2 or alkaline earth elements. Remember, these elements are similar to, but less reactive than, group 1. The big swath in the middle here, from group 3 to group 12, are our transition metals. As the name suggests, these elements are metals, and they contain many of the metals that you think of for jewelry and also industrial applications. We will skip over groups 13 and 14, which are important but don't have distinctive names, and over to group 15. Group 15, which contains nitrogen and phosphorus, are called the pnictogens. Group 16, where we have oxygen and sulfur, are the chalcogens, while my favorite group, Group 17, shares its name with a designer clothing brand, the halogens. Finally, on the end of the table at Group 18, we have the noble gases. At the bottom of the table, you'll notice that we have two periods of elements that belong in the transition metals but don't quite fit. For this reason, we've punched them out and placed them below the table in their own area. These elements are actually named by their period, not the group, and are named after the first element in that period. On the top, we have the lanthanide series, which comes from lanthanum, and at the bottom, we have the actinide series after actinium. One final classification I'd like to focus on are the physical characteristics of the elements. Specifically, a large swath of the table, which I'll highlight now, are our metals. On the right quarter or so of the table, we have our nonmetals. But we also have a class of elements called metalloids, which exhibit properties of both. They occur, predictably, at the interface of metals and nonmetals.